Experiment 5, I chose to model the falling slinky. So the purpose of this lab was to model the forces acting on a slinky dropped from static equilibrium, and using that model the motion of the slinky. And so this model was created in GlowScript, and the principle it's based off of is Newton's second law, which states that net force is equal to change in momentum with respect to time. And so using this equation, we can derive these equations, which can be used to update the velocity and the position iteratively to model the motion of an object if the forces acting upon it are known. And so the results were that for my model, the bottom of the slinky remained stationary until the top of the slinky was fully compressed. So the experimental setup was that a slinky was being held at static equilibrium, stretched out, and then the slinky is dropped. And so in this case, the system is the slinky itself, and the surroundings are earth and, I forgot to mention this, but air. So let's see. This is the actual experiment, and as you can see, the top of the slinky falls until it reaches the bottom, it's fully compressed, and then it all falls as one. And so I manually tracked the position data for that experiment, and using the experimental conditions, I set up the initial conditions for my code. So I just guessed at the mass. The initial position vector, this is from my tracking data, just how I set it up. And the initial velocity is 0 because it was dropped from rest. And so the drag coefficient, I just found this by guessing and checking. I did the rest of my model and then went back and changed the drag coefficient until I found one that best matched the experimental data. And so this code had to be split into two parts because the net forces change when initially the top of the slinky is falling towards the bottom. That's one part. And then when it's compressed and all falling together, that's another part because there are different forces acting there. So in the first part, I calculated the net force, which is gravitational force, and the tension force from the top of the slinky, the stretched out part on the bottom of the slinky. And so using that, updated the velocity and updated the position until it reached the point where the top had fully compressed. And that's when I switched to this loop, which is the whole slinky compressed and falling. And so here, the forces, there's no more tension force from the top of the slinky. So the forces are the gravitational force, and then as it's falling, there is a drag force from the air resistance. And so that was the net force. Updated the velocity, updated the position, and so that was how I got my predicted position data for the same experiment. And so here was the observed versus predicted y position versus time. And so as you can see at the very beginning, it's the exact same because the slinky was completely stationary, so there's no fluctuations to measure. And here it follows the same general trend, but there is some slight fluctuation here. And so part of that is just the error from manually tracking. I can't get it exactly in the middle of the center of mass of the slinky. And another potential source of error is, like I said, I had to guess and check for the drag coefficient. And so I don't have the exact mass, the exact drag coefficient. So that is going to cause some differences between the experimental and predicted data. But you see the same general trend, which is that once the top of the slinky is fully compressed, the bottom is stationary till here, and then it starts falling once fully compressed. And so, quick discussion, why does the bottom of the slinky stay stationary? And so that's because when the top of the slinky is falling towards the bottom, it's exerting a tension force on the bottom of the slinky. So the bottom of the slinky has two forces acting on it, gravitational force and tension force from the top. And they are equal and opposite in magnitude, which means that there is no change in velocity since it's already at rest velocity of 0. So yeah.